Here's some help with using VSEPR theory to predict molecular shapes. So at first sight, it may not seem that shapes have meaning, but they do because they tell you how an object fits into the world. That's true on a macroscopic level, and it's also true on a molecular level. So, the way we're going to predict molecular shapes to see how molecular objects fit into the world around them is to use a theory called VSEPR theory. This is an acronym. The VS stands for the valence shell. Electrons, here the blue dots in this diagram, wrap around the nucleus of an atom in layers, kind of like layers in an onion. And it's the outermost layer that's going to determine the shape of a molecule. That outermost layer is called the valence shell. That outermost layer, the electrons in that outermost layer pair up with unpaired electrons from other atoms. And so those pairs are going to be in molecules. So those valence shell electron pairs are going to be present anytime you have a molecule. Now, these atoms, the electrons here, are going to repel each other, push each other apart. They're going to try to get as much space from each other as they possibly can. And it's the repulsion of each of those bonds, each of those electrons, those electron pairs, one against the other, that determines the overall shape of a molecule. So we're going to use valence shell electron pairs, the electron pairs on the very outside of an atom, the central atom in a molecule, to determine the overall shape of the molecule. For example, let's say we had a central atom, here that would be A, and we have two atoms bonded to it. Those two atoms would push each other apart just like two balloons would push each other apart. And you can see here that when two balloons are tied to a center, they push each other apart so that they are linear. So when you have one central atom and two atoms bonded to it, you get a linear shape. And you can get molecules that would look something like this. So the atom would be in the center, and each of these atoms push each other apart just like these two balloons to give you a linear shape. Now if you had a central atom, so A here, and three atoms bonded to it, then you would get a shape like these balloons, each of which push each other against each other. That shape is called trigonal planar. It's trigonal because it's in the shape of a triangle, and it's planar because no balloons are coming straight up or going down. They're all in a horizontal plane. And so you'd get molecules that look something like this. So if you have a central atom and three atoms bonded to it, the shape is going to be trigonal planar. If you have a central atom and four atoms bonded to it, so four X's here, then the shape you get is this. The four atoms push each other apart just like the four balloons here are pushing each other apart, and that shape is called tetrahedral. Now it's called tetrahedral because that shape has four sides, as you can see here. And the prefix tetra means four. So, if you have a central atom and four things bonded to it, the shape is going to be tetrahedral. If you have a central atom and five things bonded to it, then it'll form this shape. The five things will push each other apart just like these five balloons are pushing each other apart. And that shape is trigonal bipyramidal. So it's bipyramidal because if you look, you can kind of see how this top part forms a pyramid. This would be the base right here, and then it can go up to form a pyramid. There's one pyramid that's pointing up. There's another pyramid that's pointing down. This would be like the tip of the pyramid, and it's going down there. So that's two pyramids, one pointing up, one pointing down, so bipyramidal. And the bases of those pyramids is a triangle. So trigonal bipyramidal. So if you have a central atom with five things around it, five atoms bonded to it, the shape is going to be trigonal bipyramidal. If you have a central atom with six things bonded to it, then it will form this shape. The atoms will push each other apart just like these six balloons are pushing each other apart, and that shape is called octahedral. Now it's called octahedral because it has 8 sides, as you can see from this demonstration. So, if we have a central atom with 8 atoms bonded to it, the shape is going to be octahedral. Now, there are variations on these fundamental shapes that you would get if you replace an atom bonded to the central atom with a lone pair. 2 electrons on the central atom that are not bonded to another atom. So, for example, let's say we take that trigonal planar molecule we saw before, and we replace one of the atoms, so in this case the red little ball there, we're going to replace that with a lone pair, so there wouldn't be an atom there. In that case, and here we see the lone pair, it's those 2 dots. So in that case, we get a new shape, and the shape is called V-shaped. We can do a similar thing with the tetrahedral molecule. If we take this tetrahedral molecule and we replace one of the bonds with a lone pair, we get a new shape, and this shape is called trigonal pyramidal. Pyramidal because it kind of looks like a pyramid, and then trigonal because the base of this pyramid is a triangle. Now if we take another bond here and we replace it with a second lone pair, then we get yet a new shape, and this shape is bent. So if you ever have 2 bonds and 2 lone pairs, the shape will be bent. We can do a similar thing with the trigonal bipyramidal molecule. So if we take that trigonal bipyramidal molecule and we replace one of the bonds, one of the atoms, with a lone pair, you get a new shape, and the shape is called seesaw. Now it's called seesaw for the reason you can see in this demonstration. You can put it down and sort of treat it like a seesaw. If we take that seesaw shape and we replace one of the atoms there with a lone pair, we'll get a new shape called T-shaped. So if you ever have 3 atoms and 2 lone pairs, the shape will be T-shaped. And if we replace one of those bonds with a third lone pair, the shape would be linear. So if you ever have 2 bonds and 3 lone pairs, the shape is linear. Last but not least, we can do this with octahedral. So if you have an octahedral molecule and you replace one of the bonds with a lone pair, then you would get a shape that's called square pyramidal. And so you can see how it kind of forms a pyramid whose base is a square. So square pyramidal. If we take one of those bonds and replace it with a second lone pair, then we get a shape that's called square planar. So it's in the shape of a square, and there's nothing going up or down, so it's all in one plane. So if you ever have 4 atoms and 2 lone pairs, it's going to be square planar. And that gives us our table for the possible shapes we can get for these small molecules. So our first step to predict the shape of a molecule is going to be to draw the Lewis dot structure. And based on the combination of the number of bonds and the number of lone pairs, we can use this table to predict the shape. So let's do that. Here the question says, what shape would each of the following molecules have according to VSEPR theory? And we'll start with NH3, or ammonia. So in this molecule we have 1 nitrogen, so we'll draw 1 N. Because nitrogen is in column 5A, it's going to have 5 valence electrons. So we put 1 on each side before we start pairing them, so that gives us 5. Now we have 3 hydrogens. I'm going to put a hydrogen on each side of the nitrogen that has an unpaired electron, so 1 on the right, 1 on the bottom, 1 on the left. Because hydrogen is in column 1A, it's only going to have 1 valence electron. So I'll put 1 dot on each of these hydrogens, and I'll put it on the side that's facing the nitrogen. Okay, now on nitrogen we have 3 unpaired electrons, and on each hydrogen we have 1 unpaired electrons. Unpaired electrons are unstable, and so they're going to pair up in order to become more stable. So those 2 can pair up, these 2 can pair up, and those 2 can pair up. Now those paired electrons are making these atoms stick together. They're making the hydrogen bind to the nitrogen. And so they're called bonds. And because they have that unique function, they're drawn in a unique way. Instead of the two dots, they're going to be drawn as a line. So that line represents those two dots. And we can replace each of the two dots that are being shared with a line or a bond. So this is our Lewis dot structure. Now, in this Lewis dot structure, we have 3 atoms bonded to the central atom, the nitrogen, and 1 lone pair. So if we go to our table, which shape has 3 atoms and 1 lone pair? It is that one right there. That is trigonal pyramidal. We have 3 atoms, the 3 x's, and 1 lone pair. Each pair of dots, each 2 dots right there is 1 lone pair. So the shape that NH3 would have would be trigonal pyramidal. So if you take nitrogen, which makes up 79% of our atmosphere, and you react it with hydrogen, which makes up the gas clouds in outer space, is the main component in them, and you react it in just the right way, you get ammonia, and ammonia, the shape of that molecule is trigonal pyramidal. How about CO2? What shape would we get for that? So first let's draw the Lewis dot structure. We have 1 carbon, so I'll draw carbon. Carbon is in column 4A, so I'm going to draw 4 valence electrons around it. 1, 2, 3, 4. I have 2 oxygens, so I'll draw 2 oxygens. Oxygen is in column 6A, so I'm going to draw 6 valence electrons around each oxygen. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Now we have 4 unpaired electrons around the carbon, and we have 2 unpaired electrons around each oxygen. So unpaired electrons are unstable. We're going to pair them up to make them more stable. So we can pair these 2, we can pair those 2, and remember, paired electrons are bonds, so we can rewrite them as a line. Now we still have unpaired electrons, so we can pair those up again. So these can be paired and those can be paired, and we can redraw paired electrons as lines. So 1 line and 2 lines. Alright, so this is our Lewis dot structure for CO2. Now, carbon is the central atom. Around carbon, we have 2 atoms and 0 lone pairs. There are no dots on carbon. So what shape has 2 atoms and 0 lone pairs? Linear. And so the shape of this molecule is going to be linear. So if you take carbon, and here I have it as graphite, and you react it with oxygen, and this is liquid oxygen, in just the right way you would get carbon dioxide. Here you have dry ice, and here you have the carbon dioxide being released above a candle, and those are all linear molecules. So anywhere where you have carbon dioxide, you have linear molecules. So in every exhalation you have, in every bubble in a soda, or pop in champagne, or fizz in a beer, and every time you've seen dry ice, they've all been linear molecules surrounding you. Let's try the shape for this molecule. So for silicon, we only have 1. And silicon, because silicon is in column 4A, it's going to have 4 valence electrons. So I'm going to draw 4 dots. 1, 2, 3, 4. Now I have 2 fluorines. So I'll draw 2 fluorines. And fluorine is in column 7A, so I'm going to draw 7 dots around the fluorine, 7 valence electrons around it. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, now I have 2 chlorines, and I'm going to put the chlorines on the sides of silicon that have unpaired electrons. So 1 there, 1 on top. Because chlorine is in column 7A, it's going to have 7 valence electrons, so I'm going to put 7 dots around that. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Alright, so those are the dot structures for each of those atoms. Now around silicon, we have 4 unpaired electrons. Around each fluorine, we have 1 unpaired electron. And around each chlorine, we have 1 unpaired electron. So those are unstable, and to become more stable, they're going to pair up. So these will pair, those will pair, those will pair, and those will pair. Now those paired electrons are binding those atoms together, so we can redraw them as lines or bonds. So that's a bond, that's a bond, that is a bond, and that is a bond. And that is our Lewis dot structure for this molecule. Our central atom is silicon. Around that atom we have 4 atoms and 0 lone pairs. So what shape has 4 atoms and 0 lone pairs? Tetrahedral. You can see that around that central atom you have 4 atoms, 4 X's, and 0 dots, 0 lone pairs. So the shape for this molecule is tetrahedral. So if you were to take silicon and react it with fluorine and chlorine in just the right way, you would get this clear gas, and it would have a tetrahedral shape. How about C2H2? Let's try to figure out the shape of that. So we have 2 carbons. I'm going to draw 2 carbons. Because carbon is in column 4A, it's going to have, each carbon will have 4 valence electrons. So I'm going to put 4 dots around each one. 1, 2, 3, 4. 1, 2, 3, 4. Now we have 2 hydrogens, so I'll draw 2 hydrogens in. And because hydrogen is in column 1A, those hydrogens are only going to have 1 valence electron. So I'll put 1 dot on each of those. Now, around each carbon we have 4 valence electrons, or 4 electrons that are unpaired. So those unpaired electrons are unstable, and around each hydrogen we have 1 electron that's unpaired. So these are going to try to pair up to become more stable. So we can pair those and those and those. They're more stable, they make the atoms stick together, so they're bonds. We can redraw them as lines. Now you can see we still have some unpaired electrons, so we can pair those up to make them more stable, and we replace those paired electrons with a line. So this is our Lewis dot structure for C2H2. Now, if we pick one of the central atoms, one of the carbons, let's pick this carbon right here, around that we have 2 atoms and 0 lone pairs. So, what shape has 2 atoms and 0 lone pairs around a central atom? Linear is the shape. So this molecule is linear. So if you were to take carbon, which depending on how it's squeezed could either be charcoal or graphite or diamond, and you react it with hydrogen, which we said form those gas clouds in outer space, you can get this linear molecule, C2H2, which is called acetylene, and it's used in welding. It's what's burned to make those hot flames in welding, and you can see that it's linear. How about Ch4 Methane? What's the shape of that? So we have 1 carbon, so we'll draw C. Because carbon is in column 4A, we're going to draw 4 dots around it, so 1, 2, 3, 4. We have 4 hydrogens, so we'll put 1 hydrogen on each side of the carbon. Because hydrogen is in column 1A, each of those hydrogens is going to have 1 dot around it, or 1 valence electron. So 1 around each of those. Now around carbon, we have 4 unpaired electrons. And around hydrogen, each hydrogen, we have 1 unpaired electron. So those unpaired electrons are unstable, so they're going to pair up to become more stable. So we can pair each of those. Those paired electrons are binding the atoms together, so they're bonds, and we can redraw them as lines to show that unique function. So our central atom here is the carbon. Around that atom, we have 4 atoms bonded, and 0 lone pairs. So what shape is 4 atoms and 0 lone pairs? That shape is tetrahedral. So methane, CH4, is tetrahedral. So if you were to take carbon and react it with hydrogen, you would get CH4 molecules, and those would be tetrahedral. Now methane, there are a lot of microbes that when different creatures die and the microbes decompose their bodies, they'll release methane gas. So in these lakes, when fish and other creatures in the lakes would die, they'll sink to the bottom, and the microbes at the beds of these lakes will then decompose the bodies and release methane gas, and those gases will bubble up to the surface. In the wintertime, as the lake freezes, it freezes the bubbles inside, and so these are frozen methane bubbles in Abraham Lake in Canada, and they're full of tetrahedral molecules. Now that can also happen underneath permafrost, which is a thin layer of ice in the ground. In Siberia, as creatures die underneath that ice, these microbes will decompose them and produce the methane gas, and then bubbles of this methane gas will get stuck underneath the permafrost, and it'll form bubbles like that. They can get pretty big, and when they pop, they look something like this. They're not only on Earth, they're also in outer space. This is a moon called Titan in our solar system, and it has oceans of methane on its surface, full of tetrahedral molecules. Alright, last but not least, let's try to figure out the shape of water, H2O. We have two hydrogens, so I'll draw two hydrogens. Because hydrogen is in column 1A, each of those hydrogens is going to have one valence electron. So I'll put one dot on each of those. We have one oxygen, so I'll just draw one O. Oxygen is in column 6A, so I'm going to draw 6 dots around it, 6 valence electrons. So 1, 2, 3, 4, 5, 6. Now around oxygen we have 2 unpaired electrons, and around each hydrogen we have 1 unpaired electron. Those unpaired electrons are unstable, so they can pair up to become more stable, and we can redraw those electrons that are making those atoms bind together as lines or bonds. And so that's the Lewis dot structure for water. Oxygen is the central atom, and around that central atom we have 2 atoms and 2 lone pairs. So what shape has 2 atoms and 2 lone pairs? Bent. Bent has these 2 atoms, the 2 X's, and the 2 lone pairs, so this one right here and that other one. And so the shape of water is bent. So if you were to take hydrogen and react it with oxygen, and here you have liquid oxygen, which is magnetic, you can see it attracted to the poles of these magnets. If you react these two together in just the right way, you get water, and water is a bent molecule. Thanks so much for your attention.